Well, hi, good morning, and thanks so much for joining me in my shop here today on September 8th. September 8th, right. Okay, just before I get going on the radio here, just a comment about video making and video posting in particular. A couple days ago, I noticed for the first time, and kicked me in the rear, having been doing this for years and only noticing now, that YouTube prepares the SD, the standard definition version of a new video quickly, but it doesn't prepare the HD version of it so quickly. And I've been trying my best to post these videos as quickly as I can after I have them ready. Try to do them the same day, so I do the work in the morning and posting the video, dinner time or something like that. That's kind of my goal. What I've realized, unfortunately, is if I rush the posting of the video, there's a chance the HD version is not available. And I know there's about 150 of you who watch my videos pretty quick after I post them. There's a good chance what you're seeing is only the SD version, and the HD version is just not available yet. So what I've taken to doing now is delaying the posting of my video. And so I'm trying to work that into a sensible process. What's happening, in fact, is I'm not posting it when I would normally. I see only the SD version is available, and then I walk away and forget all about this for the rest of the day, and I get it posted the next morning. That's what's kind of happening here. So keep your eyes open. You can always check to see what definition versions are available. There's a little gear you can click on. You can look and see what versions are available. So yeah, but I'll do my best to not post them that quick anymore. We'll see how that goes. I'll probably forget this whole thing tomorrow, and that's the end of that. Okay, over to the radio here. What's up for today? Well, right away, hey, I missed a capacitor. This one right here. We're going to look on a schematic where this is. This is quite an important capacitor, and it's a big one, physically big. Capacitance is relatively big. Big part doing a big job. So this might make a significant improvement in the radio. Even though now, hey, it's working. Great. And I think now might be a good time to check some of these high wattage resistors. There's one sticking out right here. There's another one in here. Just take a quick look with an ohm meter and see if that test alone suggests there's a problem with those big wattage resistors. The next thing then is to fire up the radio and operate it after this has been changed. And then take an inventory of its operation, just run through the bands, give it some signals from the signal generator, and just find out if all the bands are functioning and just what's going on with this radio. Basically, that's the idea. That might be the end of today, or the next step after that is to go through the alignment of the radio. So, okay, so today is still, I guess I'm still in cleanup mode. And really, the first thing I want to do is get rid of this capacitor up here. So I put a clip lead on it yesterday so I wouldn't forget today. I almost forgot why the clip lead was there. So this is a capacitor from the first IF transformer to the chassis. So it's a drainer capacitor, or a quieter, levelizer. Okay, what do you say? What do you say, Mr. Capacitor? Okay, so there, I think I can see it there. You don't want to scrape these too hard. When you scrape them, you will scrape the numbers right off. Quite sure what I'm seeing there. Let me just change the focus on this camera. Just hang on a second here. Mouse clicking away as I'm calling up the dialog box for that camera. I'm just forcing the focus up. W10. 400.2. So here's where it is. 0.02. I thought I saw 0.025. Didn't I see that? But 0.02 is fine. 0.02, 400 volt. What's the W10? I don't know. 0.2. 0.2. Is that? No, 0.2, 0.4? What is the 4 there? What's the 4 for? Well, I think it's a dash. I think it's 0.02 dash 400 volt W10, whatever W10 is. And we know from experience now just how fragile these capacitors really are. Terrible looking, isn't it? Okay, so a 0.2. Let's look on the schematic here. So we're working at we're working at the first transformer, and off of one of these 4 wires is going to be a capacitor to ground. Wow. Oh my gosh, this is just going everywhere. Tell me that's one there. Way over here. No, capacitor to ground. That's a ground right on this wire. Did I mistrace it? Let me try that one more time. There should not be a ground on this wire, that's for sure. Well, you know, I don't think there's a connection here. There has to be a connection. Oh my gosh. Look at how they've drawn it. Put pretty nice dots where there's connections, and you know, these photocopies and that can kind of box up a spot here where wires are crossing on the diagram and make it look like there's a dot there. I don't think it's connected here. That's a terrible, terrible way to draw it. Okay, so assuming, well, what goes out this way? Oh my gosh, this just goes on forever. Oh, it's the B plus line. That makes sense, doesn't it? Oop. Well, the capacitor is connected right at the transformer here. Did I actually follow the right wire? Oh, here we are. Here we are. Right here. Yeah, those just must be crossings on this diagram. Okay, this be the guy. And it's 0.2. It's 0.2. There you are. C30, 0.2, 400 volt. It's exactly what's there. And what is it doing? Oh, it's got a very important job here of trying to provide a signal ground at the bottom of this coil. And this one too. So if this capacitor is not capacitoring very well, if it doesn't have much capacity, then you won't get a ground here. It can only weaken this whole thing. Great. If it was leaky, you know what? You're trying to put B plus. It's going through the coil here, the DC. B plus onto plates. So I mean, there's a large voltage here, and that's why they darkened or blackened or heavied up this line to indicate that. In fact, any capacitor with a heavy black line coming to one side is under stress. That's interesting. Like this one, which I will have changed. Okay. That's interesting. You know what? It might be worth playing the radio, listening to it, getting something stabilized, changing this capacitor and seeing what happens. I think I'd like to do that. This is the lone bad capacitor. Well, I'm hoping that's the lone bad capacitor in this radio now. Well, maybe I was a little overzealous, because as soon as I stopped the camera and turned on some of the equipment, I thought, well, instead of just standing here waiting for things to settle down, I might as well change that capacitor. So I did, and then I realized, no, the whole idea was not to change out this capacitor, but to test the radio and then change it out. I missed another opportunity like that. Doggone. I think when I'm doing these videos, I often say, and I'm going to do this, and then I never do it. Yeah. So let's test this guy anyway, and we'll see what condition it's in. Just scraping the leads a little bit. Over you come. So the kind of test I'm performing here, which is applying a voltage and then measuring or having the eye respond to any leakage current, is a test designed for these old higher voltage capacitors. Newer equipment, especially the very new equipment, computerized equipment, chips, all that kind of stuff. No high voltages in there. And the idea of testing a capacitor from one of those things with high voltage is a little bit odd. And today they use other tests. ESR is more important for the tiny components, I believe. That's the deal. Okay, here we go. 50 volts. What's it do? Oh my gosh, it worked great. Wow, that's an excellent result. Wow, totally surprised. Let's give it the 400 volter. Let's give it. Okay, so not so great at 150 volts. So a brand new capacitor, I can crank this thing right up to 450 on those new yellow capacitors, and there's zero leakage on the meter. So okay, some leakage, but not the worst. And again, what the real capacitance is of this capacitor, I can't really tell. It's enough of a leak in it that the measurement will show high. It will show almost certainly more than 0.2. And I don't believe it. So, okay, we're all set here. Now, I was going to test the resistances of some of these resistors before we turn the set on. Not a particularly good idea to try this with it operating. Okay, wait a minute, that's not right. So the first one will be this one. I see there. I see a silver end, see a red body, but the dot in the middle here, who knows? It's all roughed up. Barely fits. Oh, we've got to be able to see the meter here. I'm going to guess it's some hundreds of ohms. So we get 230 ohms there. That's on one of the output tubes. 230 ohms, that's probably a cathode resistor shared by those two guys. So let's take a look and see what we can see here. So we're looking for this. Look at that. This is looks like 230, 220. 2 watts. So it's perfect. That's fine. There's no reason to change that. Okay, great. Oh, look at that. I still have the secondary image up there. Great. Well, that's perfect. Now, there's another big guy here. Let's see what he measures out at. More than 2,000. Pretty sure I've got it up here. More than 20,000. That doesn't sound particularly good. This is also, there's a big one. It's tied to one of the terminals of the IF transformer here. A big wattage resistor on the first IF. What's going on here? Looks like it's going to a terminal of this too. Oh, my poor cat. My poor cat is yelling at me out here. Yes, Shadow, what's up? Yes? I need a little more information. Do you want to go in the garage? You want to go in the garage? Yes, Rio. Okay, well, we won't be hearing from her again. She's in the garage. That's not a punishment. They like to go in the garage, my two cats. Where are we at here? Oh, yeah. So we're going to try to locate this. It was on one terminal. So it's on one of these terminals. So here we go. Not the top. Not there. That's says half watt. Oh my gosh. We're going on this long journey again. Here's a 2 watt. Some thousands. This is it here. What? R11. Well, who's meowing? What? Who's meowing at me now? You want to go out? To the garage? Okay. Come on. Come on. Well, they're a little, well, they tussle out there. The poor guys, they want to be outside, but it's rainy today. Isn't that right? Okay, two confused cats. They don't know what to do. They don't know what to do with themselves. Now I'm off here again. Oh yeah, so we think this is probably correct. Let me read it again. On the 20,000 volt scale here. It is in circuit, which means if I get a wrong reading, it's going to be less than what it really is. It can't be more. This is definitely the right terminal. Getting over 20K. Over 20K. Is this really that resistor? 20, so I'm at 21,000 ohms. Brown. Okay, brown to start. Brown, I don't see any red. The dot could be hidden. Body and dot. Body and, well, I don't know what that is. Brown, black, who knows what that is, for crying out loud. And it could be just discolored from heat also. It could have been red at one time and now it looks brown. Okay, so the other end of it though goes right onto a tube terminal, and that would be pin number 876. 6 of the, what is that? 6 of a 6SK7. That's a plate, isn't it? Isn't that what that is? 6SK7. 6SK7, pin number 6. No, 6 is the screen. So it's a great big screen resistor. So those could be a little larger, I think. Let's look now. Let's study up on the schematic here again, which you may have been doing. Yeah, pointer is the mouse. So off the screen of this tube. Why did I think I was looking at this resistor earlier and had found it? What's happened here? I kind of lost my mind here, did I? Off the first IF, I have lost my mind. It comes off of one terminal of the IF and heads to pin 6. Pin 6 is the plate that has to be here. There's nothing here. How does this work? How do you get a big resistor in here? And what happened to the one I saw? I just totally lost track of it. Because it was stuck way down here. Here it is. Okay, so we try again. Coming off one of these. How about this one? No. It's going to be the plate. It's going to be off of here, actually. Off this plate of this tube. But it would be tied here. Screen, Jim, screen. Where's the screen here? Gotta be this line here. There's the 0.2. No, that's 0.2 here. Ooh, I'm getting all mixed up. Yikes. So is this the screen line? It's too bad these tubes are all blacked out here. It's going into each tube. And then it finds its way back to B plus through this resistor. That for sure is a screen line. And what's this? This is probably screen. Oh, another filter on it. Right, filtering capacitor and the resistor, Jim, resistor. My head's getting all mixed up here. Well, okay, so what's that say? Does that say 2,000? Or does it say 12,000? What does it say? 1,000. Does it say that? I don't think we can read this. Oh my gosh. So now it's down to, is this 2 digits or 1? So there's a number 2 right there. This doesn't look like the 2. Son of a gun. How am I going to figure this out? Leave it alone. It's 20,000 ohms. 20,000 ohms. Plate a screen current. Screens carry a fair bit of current. Well, you know what I could do? I could measure the screen voltage out here, and if it's low, then we take action. If it's not low, we don't worry about it. And what should it be? What should it be? A sudden breakthrough here. It's not written here anywhere, is it? So it should be something a little bit less than the B+. So we measure the B+, we should find screen a little bit below it. If we stick with the IF tube, puts this one up here, it's right out there. I can see all the terminals quite easily. So what we'll do is we'll check the voltage. There must be another wire. Yeah, there's another wire on the other end of this terminal. Yeah, okay. We'll just check the screen voltage, which should be here. This is the screen voltage. Why is this? It's picking up the plate voltage and screenalizing it through this resistor to make it into a suitable screen voltage, which is then spread through the tubes. We should find full B plus here and then screen voltage on this end. That's what I think. Hey, everything I say, I'm taking with a grain of salt. I don't know if you realize it. I may sound like I really know for sure what I'm doing, but everything I say, I go, yeah. In my head, I'm going, yeah, sure. That's experience talking. Okay, let's fire up the radio and see what we got with this new capacitor here. Might be in for a very pleasant surprise. Oh, okay, the cats may have confused me a bit on the video here. I may have made a video recording error, so I'm just going to repeat something. And that is, I'm going to check for the voltage on either side of this resistor. One side should be B plus and the other side should be somewhat reduced voltage for the screen circuits in the radio. I think we're ready now. Everything is safe and ready. Away we go. Okay, normal dim bulb operation there. I did change a capacitor, heard pop in the radio just now. That's right, this radio, come to think of it, at the end of the last video, it didn't actually perform until something happened. I don't know what happened, but suddenly it seemed like the sensitivity came way up. Terrible noise in here. Now that noise is either being received or it's inherent. Some noise in my shop. Okay, so radio's performing. Let's do those. Let's do that measurement. Okay, one side is B plus. I think it's this side. 150 volt scale on my meter here. So we're reading just under 60. That's not very good. But I do have restricted power, 99 volts. 93 volts. But let's give it the full juice here. Full juice. Okay, so now I've got 75 here, which seems very low, but maybe this is the screen side and I got it backwards. The other side, okay, I can see the meter going right over in the corner of my eye here. So this must be the B plus side here. Okay, so I'm kind of blocking the meter. That's reading almost 250, and on the other side we're getting 75. That sounds a little low. Let's check the book. What does the book say? What does the book say about this? So we can pick any one of these tubes. We'll pick the 6K7 again. 6K7. This is the reason why you see the same sort of sets of tubes again and again in a. It's like a chip set. It's a tube set. There's certain commonalities between certain tubes, and they've all been made this way. This doesn't happen by luck. To make it easier and easier to build these radios. You know, so for instance, they all take the same screen voltage, can all be driven by the same screen circuits. That kind of thing. 6K, 6SK7, 6SK. I'll be okay. 6SK7. Now we have a Class A amplifier, which I think is how it's being used. Maximum ratings. Let's look at the maximum ratings. Plate voltage 300. It's around 250. Screen voltage C curve on page 67. This is all we got to do. We'll use this curve here. Grid number 2 supply voltage 300 maximum. Grid number 2 would be the What was that? That's a strange sound. Grid number 2 is the screen grid. So 300 max. Well, we're nowhere near that. Okay, so we'll look at this curve. Characteristics. Okay, so this is if you were to operate it. Operate it at a plate voltage of, let's say, 250. Then grid number 2 should be 100 volts. And I'm at 75. It's not so bad, is it? Transconductance, plate resistance. And what now? So if we look at this, what do we got here? We got plate, oh my gosh, plate 1, or grid milliamps. So we're looking at plate voltage, plate voltage down here. And oh, they just put the title here sideways. So plate here and grid current. Oh, how's that going to help me? Okay, so we come out here to 250. Rate just above the 240 here. I don't know how to read this. And if the grid is running properly, I think it said in the -3 up there. Yeah, grid 1 -3. I don't know if this isn't going to work for me at all. -3 is up here. So what do we got? We've got an IB. So this, if you set the bias at -3 and then you run the plate voltage up and down, you get this curve. How does this tell you screen volts? Yeah, I'm not going to get anywhere with that anyway. So we got to make a decision here. 75 or 100? 75 or 100? Let's just measure this again to be a little more sure of things. We're at full voltage. Radio's operating. B plus we know is about 250, so it's really here. So that's reading 76 volts instead of 100. I think I'm going to leave it alone for now. Because I don't know for sure what to change it to, what to install. 20,000. If it's 20,000 ohms, how can you even see anything on the other side of it? Well, they expect it to drop a fair bit of voltage. That's why it's a great big high wattage resistor. Now, is there any others in here that I need to look at? There should be a cathode resistor down here. Wasn't it this one? Wasn't that the shared cathode? Confused myself. Let's look at the schematic. Yeah, that's it, right there. Yeah, so that's fine. And it's probably bypassed by one of these, right there. And the molenode condenser appears to be okay. Radio's not really humming. I have it on its big speaker if it were humming. Where are we at now? Now we're at the run through, check of voltages on the tubes, and then we're ready for alignment. So tube voltages should be good. We're on the 150 volt scale, but there's over 250 volts in there, so we'll go on. We're on the 500 scale, so 250 straight up. The meter. There, how's that? Is that better? Not really better. That's the problem there. Lighting can be tricky business. And what you see in the camera is not what I see. It looks quite different to me. And I'm going to work in the dark here. We'll start with the two output tubes. I'll shine some light on it here. Okay, the objective is to find both the screen and plate voltages on the two output tubes. Without regard to the schematic. So there we've got a 250, that's full, pretty much full B+. Okay, same pin on the other output tube. Make sure I get the same pin here. And we get, it's not the same voltage. Let's try it again. Here's the key. 1, 2, 3. So 4, pin 4 gives me really 235 volts. These tubes are arranged exactly the same. Yeah, 1, 2, 3. This is 4. I had the wrong. I was on the wrong. That's kind of strange. Okay, so there's the same high voltage. It's strange that I got a screen voltage here. Didn't I feed it here? Hey, what's going on? Okay, so let's double check this again. 1, 2, get on 3. There we are. So 3 is showing 210. 4 is showing 230. 210, 230. This one's showing much lower, 175, and then the plate is showing the same. So the screen seems low here. Somebody's noisy. Everything's noisy. We have this capacitor here that I didn't change yet. And I had found, like on this side, screen, a lower screen voltage. What's going on between the screens of this tube that they can have different voltages on them? That would be the question. Okay, let's take a look at the schematic and see if we can figure out a difference between the two screens. Why? First of all, this is probably the screen here. No. Oops. This must be the screen. Oh, I have to play guessing games here. No, that's the cathode, because there's the cathode resistor. This is showing high voltage. It's heavied up. So we got the two high voltage, plate and screen. So look, the screens are connected solidly by a wire. Something not going right here. Something is not going right. Pins 3 and 4. On the 6F6. So that's probably one of the capacitors, the one I was poking on. And this is probably the other one. Are they the same amount? 0.00 something. 0.001. 0.00. Probably these are the two gray ones that were in there. Plate voltage on one side. So the screen voltage, wait a minute, this is across the plates. I mean, we've got a difference in plate voltage. I'm all messed up. Okay, let's take a look at the, let's see if I, okay, unmessing time. 6F6. Apparently some of you like listening to me babble like this, so that's why I put this on video. I've got numerous emails saying you enjoy listening to me think my way through these things. To me it's one non-stop embarrassment, but that's okay. As long as it works out in the end. So we're looking at a screen on 4, plate on 3. So we should be higher on 3 than 4. 4 should be tied together. And see the same voltage on 4. Okay, so 3, this is 3. 3 is the low one. 3 is coming up. Now 175 and 4 is coming up higher. The plate voltage is depressed. How can that be? Doesn't the plate, oh good, still got the schematic up. Doesn't the screen get its voltage from the plate? How did they do this exactly? So they have the B plus coming up through here somehow. Here it is. Coming up here. B plus going into the output transformer, and then B plus should be split exactly the same to this tube and that tube. It shouldn't be any different unless tube conduction is different. The tube's operating point is different, but they shouldn't be. They have the same cathode resistor, and I've changed out. So I'm thinking about blocking the grid blocking. Oh, look at that one. Okay, 0.01 I think. I think I've changed these grid blockers. They're blocking plate voltage from getting onto the grid. So going back here again. Well, that's interesting because look what the screens get their voltage straight from B plus. Whereas the plates get it through the output transformer. There can be a bit of resistance in here and a bit of a drop. So, and then where's the big 2000s over here? Oh, it's the screen of these tubes, not screen of that tube. Come on, keep your head together, Jim. So the screen would be higher in this case. Coming over here also, so this is just how the Magic Eye is getting its B+. We haven't even looked at the Magic Eye yet to see if it's even on. Well, isn't this another stupid situation to be in? So generally speaking, you do not want the screen voltage to be higher than the plate. That's what it showed in the tube manual too. Yeah. Should we consider this even a problem? Well, what am I actually chasing down here? Chasing down a difference in the screen voltages. How is that possible? I'm looking at these capacitors. I believe I'm looking at these two capacitors, the gray ones, earlier replacements, I believe. And yet I'm thinking this is going between the screens. It's going between the plates. You know what? If the voltage across this, or the voltage on this capacitor, either side, is the plate voltage. Let me check that. I'm going to check it with what's left of my head here. Either side of this little gray capacitor. You can see that? You can't quite see it. Enough already. So this side we're getting 200 on my meter. This side we're getting 175. So what's going on here? This is supposedly between the plates. Plates on 3. Oh. I should write all this down and have little diagrams prepared, and so I can quick reference them instead of doing this all the time. E, F, G, H, I, J. 6F6, output 2, Yeah, plate on 3. Plate on 3. Capacitor's on 3. That's the capacitor between the plates. You would expect it to have the same voltage on either side. Double checking again. So, whoa. So here I'm getting, I know you can't see it, but you have to trust me. This is the 175, and on this side. So now I did test these tubes and they did not match. They're not a matched set of tubes. So their mutual conductance is different. So that would mean their operating condition would be different. The quiescent current going through them would be different. That shouldn't make any real difference here unless it's huge, because you'd have to have a huge current flowing in the winding of the output transformer to cause a significant voltage drop. So this is one of the challenges here at this point with all this radio work is current measurement, current flow in plate connections, and that not the easiest thing to determine. These two tubes are working in push-pull, but they're sharing a cathode resistor, so we can't see too much there in terms of, you know, we can see the current flow, the sum of the current flow through the two tubes, but we don't know which one's which. And the current coming back. So measuring the two plate voltages is measuring the output, the DC that's making it through the output transformer. And that's exactly what I'm doing here. Now, is the difference anything to worry about? What other voltages are not the same on these tubes? So if we look at the screen, again, yeah, screen being higher, and it kind of has to be, I guess, 230, and the screen down here, 230 is exactly the same. Screens are basically connected by a wire. Imbalanced current flow through through the two output tubes is causing an imbalance in the plate voltage. The imbalance in the current probably caused by differences in the tubes. The tubes are not matching, so their current flow is different. Now, it doesn't implicate these two capacitors at all. Ooh, so I just hit something, and instead of just hearing a noise, there's a continuing sound. There it is. It could be anything around here. I mean, everything's making noise. That's interesting. What is it? Stay there. Don't stop. So what I did there was I pushed on the bottom of one of the tubes, you know, the key that sticks through. I just pushed on it slightly. So I'm going to grab that tube at the top here. Try not to sizzle my hands and wiggle it, if I can do it. Okay, I'm trying to get a hold of it here. Here we go. Okay, I'm holding it. What was that? I'm bumping something else with my arm. It's coming and going. Wow. Those are the output tubes I'm tapping. This one's very, very, very. I think it's this. Sounded like a radio reception there for a moment. I think that too. Now is this also the weak one? They got it. Yeah, that's a rectifier tube at the bottom anyway. So either that tube, I could swap them. Yeah, swap them and see it. Hey, bingo! Swap those tubes. Swap those tubes. See if the voltage flips around. Now, just to be absolutely sure, flips around in my head all the time. So that's the low side. Try again. So that's now reading just under 200, and this is reading. Yeah, this is lower. This is lower than this. Radio off. Those tubes are scaldingly hot, so I'm going to let this cool off a bit before I try pulling them out. And we'll flip them around and see what happens. Okay, like the numbskull I often am in here, I pulled the two tubes out and then immediately lost track of which one came from what socket. So in terms of putting them back in the other way, so I decided instead I'm going to put these through the tube tester and carefully make notes about each one of them so we know what the differences is as far as the tube tester is concerned. Then we'll put them back in the radio and carry on with experimenting here. Well, I wasn't going to record any of the tube testing because I tested these tubes before, but as soon as I went to do the short test on this tube, to position number 5, so that's up a little bit. That's not its normal spot. That's more normal. And the first time I did this was much higher. Wonder which tube is noisy? Now, is that a socket problem? I don't think so. Better not put this tube back in with a short in it. So this one is the Marconi, and I don't know. Is this out of my collection? I don't know anymore. If we're gonna say Marconi short on 5, partial short, leak. Let's call it a leak. Leak on 5. Leak on test number 5. Leak on test number 5. I'm making notes. Yes, it's actually making notes. Okay, good. Now, this guy. Okay, that's normal. GM on this tube is, to get the actual GM though, we actually have to multiply the reading by 2. It has to come up above 830 on the scale. There we go. Well, that's really good. No doubt about it. That is a good one. Oh, good. Yeah, good. Don't push your leg. Good one here. So the good one is going to go right back in the radio. Now, what am I going to do? Have I got any good ones now? Any more good ones? So I've been reading up on substitutes. I have many 6V6s. The 6V6 looks like a possible replacement for 6F6. So I think now this is the original 6F6 that I rejected. 6F6E. Oh no, this is the E one. We can't use it. Yeah, that's why I rejected it. That's right. And then I have this one, which turned out to be a dud. But let's try it again. Oh, it's got no key anyway. I forget it. Okay, where are we at? We're in a bad way now. We're down to 6F6, 2. So I'm going to think about that 6V6 replacement idea. It has to do with a big variation in the grid biasing. Grid biasing on the 6F6 is like 22 volts, and on the 6V6 it's half that. So if you over bias the tube, you drive it into cutoff or get distortions or who knows. It looks like it's something you could try and see how it works out. I'm going to ponder that. 6V6s. Okay, so I read a little more about what people say about using 6V6 tubes, and I think it's worth trying. It should work. This is a push-pull radio. The biasing is probably okay, but we can always check it and see what it actually is. If this tube gets biased too high, if it's too much of a negative bias on the grit, all that happens is the tube won't be as strong in its operation, and it may get driven into cutoff. And why am I moving the camera over here? What was I thinking of doing? Oh, yeah, we're going to look at my computer screen, but not with the camera. No, not with a camera. So I've been doing a lot of tube testing over the last year, and I've tested most of my major tubes, if I can call them that, and I've kept records of them. So this is my record of 6V6s that were in that tub you can see in the camera. I've got 15 of them, and I just want to pick two. There's one at 1700. Now up here is the reject number, and this is the tester I did it on. So anything under 1220 is to be rejected. So even though I have these tubes, I've kept them because they work. They don't work all that well. So that's basically the highest mutual conductance here would be best. But 9 and 11 are exactly 14 each. Why don't we try that? We'll pick 9, tube 9 and tube 11. Okay, tube 9, tube 11. Tube 9 and 11. Tube 9 and tube 11. Did I confuse myself just now? No, 9 and 11. That's what we're after. Very good. So we're gonna. These can just go right in. They have the same pin out, and that the plate. I think has the same maximum rating, just over 300. We're just going to draw. I'm not going to test these again. And make sure they are 6V6s. We're going to drop them in, and we're going to try this radio. And you can't mix two different tubes, that's for sure. That's not going to work out well. So these tubes draw much less current on the heaters too, which is actually an advantage to the radio, because there's going to be less current going through the big power transformer. That's just going to cool that down just a wee bit. Probably having an eyeball on those light bulbs is a good idea during this. Volume down. Good. Let's power up. Here we go. Here we go. Pretty normal looking bulb operation there. Everything appears normal. We're on the broadcast band. Give it a bit of volume. Come on, baby. Now I'm hooked up to the outdoor antenna. Right, because we were hearing that. Here it comes. If anything, it's the same or slightly better. But you know, these bulbs look just a little bit brighter. And what's the voltage here? 96 volts. So with the restriction on, we're just going to try to measure the plate bias, or I'm sorry, the tube bias, by measuring the drop on the cathode resistor here. Mr. Cathode Resistor. It was this one, and voltmeter. Yes, since the last video clip, between the last video clip and this one, I've done all kinds of stuff, been out to the store, all kinds of stuff. Now we're going to look on here and try to spot the, where are we going to look? We're going to look at that meter. That voltage is the bias. Careful, man. So we're seeing it, I'm on the 15 volt scale. It's up around 12. 12 on a 66. That didn't sound so bad. Let's see where we're at here. 6V. 6V6. TU 6V 66. Beam power tube. Maximum ratings 315 on the plate. We're at 250. Screen voltage should be 285. Well, we'll check it. Typical operation at 250, the bias is supposed to be minus 12. We're right there. We're right there. Very, very good. Now, what about the variation between these two readings? Here. Okay, let's try this one here. So that's 131 volts. That's more. So it's still showing an out of balance condition. And what is the significance of that? Maybe not much at all. And the actual plate voltage over 150. Now we're on restricted power again. Okay, think of what you're doing. So the plate is coming in at just over 150. Okay, we'll give it full power. Lots more volume. Screen. So the actual operating screen voltage is 200 on this side, 240 on this side, and then plate is 240 there. So plate is stronger. Plate has more voltage on it. Good. And then down here, trying to do the same thing. Wait a minute, I got these confused, don't I? I've got these backwards. Plate is 3. This is the plate. Plate is running a lot lower than the screen still. And based on the way the circuit is laid out, it has to be that way. Just maybe we're going to overheat that. Hey, I get my thermal meter in here in a second. We'll check out for things getting hot. And what am I looking for? I don't know what I'm looking for. Let's do the heat run thing. See if anything's hot in here at this point. Okay, so we're running full voltage. It's been running for a few minutes anyway. 5 minutes, 10 minutes. So this is my thermal viewer here. And what I'm going to do is I can control what temperature causes red, or the colors on here, the color scale, color range, I guess would be the way to put it. So right now, the red is only 30 degrees. 30 degrees isn't much at all. I mean, this probe here is visible because I have my hands on it. So it's not visible to you. So this is tricky for me to do, for you to do. So I'm going to raise the red to, like, concern here would be 50 or 60. So we'll change that. I'm going to select it. We want it to go up 40, 50. So now you see the amount of red is much less. And we got to find out what those red guys are. Now this is an interesting instrument. It reports to me the highest temperature on the screen and the lowest temperature on the screen here. And this tells me the temperature of whatever's under that little plus sign right in the middle there. So for instance, my bench is 23 degrees. The floor, 19, 20 degrees. Back of my hand, 33 degrees. And notice there's no red on the screen, it's not hot enough. Okay, let's go through the radio now. You have an idea what I'm up to. So we see two distinct red things here. This one is much redder, and this is this resistor. So that's telling me that resistor is running at 70 degrees, even hotter. 70 is pretty warm. Yeah, we'll look at this resistor up here. Ooh, and it's running at, I'm reading the small red print here, 60 degrees. So it's not as hot. This guy's the hot guy. I mean, that's why the paint is coming off. Now we'll look around for other sources of heat. So the tube sockets will show up. That's a tube socket. And then if you have a hot item, this is a stupid example. Here's a hot item. Oh, this is another, just a stupid example. Get a better example. Here we are, this will be better. Okay, tube. So you're looking at a hot item, and there's a wire crossing the field of view. When you look at it on this little picture, you'll see the red thing, and then you'll see a gap in it. You have to figure out, you got to figure out what it is you're seeing in these viewers. So for instance there, you can see a big red spot and a small red spot, and what you're seeing in between is actually a wire. It's actually one of these wires, which is cooler. And okay, any more heat in here? Why would these sockets show up so hot when none others do? Okay, and that's that resistor, 62. So the two high wattage resistors are cooking away. All the other tube sockets are showing just a little bit of yellow on the screen here. It's probably not even visible. Why is this guy so hot? Is there something more going on down here? So this is the rectifier tube we're actually looking at. The two output tubes, there's no heat apparent. Why so much heat in the socket of the rectifier tube? How much heat? 54, 55 degrees. Rectifier tubes do get hot. That hot? Plenty hot. Okay, so we can actually look at the rectifier tube, or the tubes, with the viewer. Problem here is, there's you can look right through the glass just like your eyeballs, and this thing can see the element inside, and it can get a little bit confused. So first of all, these tubes are plenty hot. So let's raise up this red setting. 55, 60, 65, 70, 75, 80, 85. Way up until we just about lose the redness. Okay, it's getting up there. So things got to be pretty hot now to show red. So very interesting. So this you're looking at now, this is the rectifier tube with a wire going in front of it. See the wires? And that's causing us a bit of a slice. Then when we look at the two output tubes, what do we see? I'll do this very carefully to make sure. So that's one. That's the other. Holy smokes, what a difference. One. So this one is showing up 192 degrees. That's the top temperature. And this one, is it even going? Is this even on? Oh yeah, I can see the heater. Wow, that's a big difference, isn't it? Let's check it again. 200. 190. It's actually not that much different. Maybe it's just that I got the color setting just enough to to make this look like that. Let me drop it a little bit. No, still not showing a move. Tremendous difference here. Is it tremendous? Test it again, Jen. Okay, using the center white plus 186 on that tube, 123 down here, and then the rectifier 200. That's one of the reasons why these tubes can be large. This tube in particular, the rectifier, is a big glass bulb on it because things are pretty hot inside there. These other tubes, they're not so hot. They don't need to be so hot, so they aren't. And what do you need the hot tube for? You need a hot tube to heat up the cathode. Cathode's ability to emit electrons gets higher and higher as you make it hotter and hotter. Quite intuitive, isn't it? So if you have a tube that needs to really push the current through, you need a hot cathode. And that's what's going on with these three tubes. Well, two of them anyway. What's going on with this? Hey, let's do the tube swapping thing. Yeah, we'll do the tube swapping thing. And we'll see. I'm going to grab those. Burn the skin right off my hands here. Okay, so I'm not going to grab those and burn the skin. Oh, it's coming right through that piece of cloth. Woo! Hot baby. Now remember, both these tested identically when I did the test. And so maybe I made a mistake. Testing the tubes. Maybe they aren't the same. Wow, that is hot. That's the hot one. It is really hot. The base is really hot. Is it too hot? Is one too hot? Or is the other one too cool? Come on. Okay, did I manage to swap them around? I'm pretty sure I did. On with the power. The bulb's fine. Full power. One, two, three tubes. See, there's a little bit of red showing up now on the rectifier. How come these ones aren't getting so hot? Volume, please. They give it a little bit of time, but for some reason they look the same now. No, this one's starting to get hotter. Definitely. So interestingly enough, moving the tubes didn't move the heat. The heat is still here. That's the tube with the slightly higher. Let's check. So I'm going to look at this tube's screen voltage is 190 as I measure it, and the other, no, that's a plate voltage. That's a plate voltage. The other, so this guy has a higher plate voltage than the hot tube. Screen voltage. So it's 240, and on the hot tube, exactly the same, 240. So the only difference I'm finding, at least what I'm doing, is plate voltage, and oddly enough, the lower plate voltage, as the tube goes hotter. That's really not intuitive, is it? Yeah, definitely. So definitely this tube is running hotter. Why in the heck would that be exactly? The plates get their voltage right from the output transformer. They really can't. Defective output transformer. Not terribly likely. Could ohm out the output transformer and see if it's got a difference. Or we just ignore this and say, you know, these radios are never perfect. Everything's a little out of whack everywhere on them. Is this really something to worry about? The tube manual actually gives glass temperatures. So this one, you know, 175. Let's just see if it's given in here. 6V6. It could be because it's a heavy, it's a hot tube. 6V6. Do they quote a tube glass temperature? TUV 6V6. It would be in degrees here. No, this is not going to give the glass bulb temperature. This says a 6V6 is similar to a 6AQ5 except for a few things. And it doesn't matter, you mentioned 6F6. Well. I think what I'll do, I have a lot of 6V6s, so I'm not panicky about burning one out or something like that. But that's not really likely to happen. What we're really dealing with here is probably a case of some kind of distortion. Can't worry about that till we do a lot more with the radio. So I think what we'll do is we'll put this as an observation made, something to think about, and carry on with other aspects of the radio. Now, what was it I was going to do today was take an inventory of the radio's operation. That sounds like a great next step. Okay, so what we're looking at is the other page of the schematic which I neglected to study, and it's just loaded with voltages and current flows and all kinds of things in here that can be verified. So that's interesting. That's got to be really helpful. There's more than one radio here. This is a different radio over here. So this is my radio here. And just let me just show you this. I have a little bugaboo about using the term dummy antenna, which I think is a term for dummies. And look down here. They actually defined it. The term dummy antenna means the device which must be connected between the test oscillator output and the point of connection to the receiver in order to obtain ideal alignment. So that is what I concluded in the end a dummy antenna is. It's not an antenna. It's not dumb. It's not a dummy antenna. This vague term threw me off in the past because I read, you know, can I connect the dummy antenna, blah blah. Now I know much better. So there we go. Anyway, thank you, Mr. Writer of the schematic, for verifying what has taken me so long to figure out. Now here's all the different alignment things that have to go on. Here's the details of the dummy antenna. Different for different bands. Wow. Okay. But what are we really trying to find out here? I'm trying to find out, you know what I'm trying to find out? The type of bulb. Light bulb. Do they have it here? Anybody see a light bulb showing up? No light bulb there. What about here? No light bulbs. Okay, what about the schematic I was looking at already? Sometimes the light bulb amounts to a note. They just say, and the bulb is a number 47 or something like that. Just reading everything here. Oh, to tube heaters and dial lamps. And this is where they would have written it. If they're going to write it anywhere, they would have wrote it right there. Well, we know what it is. It's a 6.4 light bulb. Okay. I thought it might be a good idea to put good light bulbs in here now. And what I'm noticing here is if you put these long bulbs, like a 47 with a long glass bulb, the clamp here barely gets on the stick. Well, that's not so true, is it? That's not quite so true. Ultimately, this is really important to position these. And I'm thinking about switching these to a different bulb. You know, it comes with the sleeve here. What's the idea of the sleeve? So this sleeve has a split on this side, and this one up here, the split is on the other side. What's the purpose? What's the reasoning? Got to be blocking light from going somewhere, probably out the front. So this is probably correct here. This is the one that works. And I think this one will work too, but I didn't really plan to have any of this on video actually. I'll just change the light bulbs without the video running. This bulb is smashed. This bulb is shot. The glass just came disconnected from the base because of this crazy clamp on here. Crazy. Yeah, get rid of this. 6 to 8 volt Mazda 44. This is a 44, but I'm pretty sure these are 47s. This is an ever ready 6.8 volt. Doesn't give a number. No number there. How about this last bulb? This is the only one that's working. It's another 44. 44, eh? Let's see what we got here. Got 44s. Got one. Uh-oh, it doesn't feel like there's any in here either. I only have 3. Yikes. Why couldn't I use a 55? I'd like to use a 55 on here. 55 is a larger glass globe on it. The reason I like to use a 55 is I bought them for some jukebox stuff years ago. Got a whole bunch of them. They're almost never called for. Let's just check it out here. So there's a big bulbous bulb on it. I think I cannot use it. But ultimately the filament position is going to be critical in here. Oh, don't get too many of these off at once. I'll be spending time figuring out which one's which. Let's put this over here. What's the problem? Oh, okay, got it in there. So obviously one problem is you can't possibly put these sleeves over it. No reason to think 44 is the right one anyway. Put the 55 back and we'll take a look at a 47. 47 is probably the most commonly used light. What's this 51? 51 is probably wrong. It's just a smaller version of the 55. 47. Oh my gosh, I didn't think it'd be this involved. 47s. 47. So we're going to load it with 47s. The final light bulb alignment, yeah, final is the word. It's one of the last things I'll be doing. But we can start by seeing how they look here. 44s, 47s. This is the only radio I've ever seen with this kind of black bar and multiple pieces of glass down here. That's really never seen that before. And in these radios, how they look on the front, this is a big part of the radio. You know, great that it works well, but if it looks terrible. Those look nice in there. Okay, we're ready. We're almost ready. So the time of day, oh, it's 10 to noon. I've got 10 minutes before lunch. That's empty. Okay. And the remaining 10 minutes. We are all set to go. I have volume down. Band all the way to broadcast. Here we go. Dim bulb first. Sticking out a little bit. Everything fine. Full. Turn down the lights here for drama on 4. Yeah, look at that. That's hard to look at, isn't it, in the camera? I got that thing blasting at it. I think if I just swing over this way and get off the filament there. You can't see the filament. Let's go in the darkness here and see what it looks like. Oh man, look at that. And if I switch bands? And that's oh, one more light down here, but I didn't hook it up. That's super, except it's really weird that I guess it's going down, 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 and then broadcast at the end, but then they wanted to put the broadcast band right in the middle of the dial, so they put it there. Hey, let's hear it. So we are hooked up to an outdoor antenna. That weak capacitor in the antenna circuit right at the start, I bypassed it, so we're on the other side of the weak. So we're getting the most antenna signal in here. Tone controls. Ooh. That's not working too good. Other tone control. So that's the bass control that's behaving weirdly, and so those capacitors may have been stuck in there, the ones I removed by somebody thinking they were trying to fix it. Yeah, it's really not working at all. Okay. Good though. So it's not picking up 840. That's the last station I can pick up around here. Okay, we'll switch bands. Next band is the broadband from 6 megahertz to 18. Pretty quiet. That's full volume there. Okay. So this broadcast you're listening to, forgetting what he's saying, when he's quiet, you'll hear a hum come up. And then when he talks, the hum will go away. The hum is coming from his end of the works. His automatic volume system is going up. And
5 or 6 steps to you, but a gospel that they will call men to repentance and faith, and to use them, and to put your spirit upon
somebody's drifting. This radio, for sure.
Fill them in a mighty way. Give them mighty intellects. Give them great hearts.
You can hear that. Okay, that's fun. So it is receiving. This might be almost full volume though. Two other little goodies there. Ooh, there's a good one. Bright light off the camera here. Okay, well, it's working. That's really what I'm trying to do, is just prove that each band is working.
It's 9330 kilohertz on the 31.
9330. Is it because this is a spread band? The tuning is not nearly as critical. So that's a very strong station. Still needing a fair bit of volume there, as in full. Okay, what else can we get? Nobody else. Pretty quiet up there. I wonder what causes that. Why does it get... Okay, now next band. 11 megahertz. We should hear stuff on this band. We'll go up here. We should hear it. Somebody, anybody? Well. Well, it's possible there's just nothing there to hear. Now we're up on 15 megahertz here. Well, it's picking up noises anyway. You gotta love how this radio looks, though. Let me see if I can just get a stick here and block the lights. You can enjoy the band switch. That's great. That's really, really great. I like it. I like it a lot. Never seen that before. Very well done. Okay, the result of all this is the radio's working, seems to be working on all bands, has performance issues for sure. Alignment is what's next on the hit parade for sure. Once the alignment's done, then we can make another judgment about the quality of the radio's reception. Hey, we'll turn the light off there. We can camera. Focus. After the alignment, then we make another check on the radio's performance, and then we might be done. Great. Thanks a lot for watching, and I'm off to enjoy my day. You enjoy yours. See ya.